So I was at an avionics talk recently, and there was a guy up front talking about safety and mission critical software. And he was having a hard time getting his point across that software bugs matter. And so he decided to tell everyone a story. And so he said that his company had a contract for some flight software. And he laid out the amount that they were getting paid to do it, the time that they had, the size of the plane, how fast it had to go, all of this stuff. And then he says to all of them, how many of you think that your marketing department would sell this deal? And everyone raises their hand. And he says, okay, now how many of you personally think that your team could meet these deadlines? And everyone kind of puts their hand down. About 10% of the audience keeps their hands up. And then he says, all right, now how many of you would be willing to have yourself and your family on the first flight of the plane? They all kind of look around, put their hands down, except for one guy, older gentleman. And so the speaker says to him, he says, you, sir, why is it that you alone are confident enough to put your family at risk on this first flight of the plane? The man, he stands up and he says, if my team wrote this software, it would never get off the ground. So I'm here to talk to you today about how to be a little more confident in your own software, to where maybe you won't be like those people in the audience who's willing to write software for someone else but not use it for yourself. I'm going to give you a few guiding principles that if you follow, hopefully will help you out with this goal. First of them is the single responsibility principle, well-known principle. A function should do one thing and do it well. The Ariane 5 launched in 1996, but there was a flaw in the inertial reference system. They cast a 64-bit floating point number to a 16-bit signed integer, and the result overflowed. The unit that had this error sent its error information, but the other end interpreted it as regular data. 36 seconds into its initial flight, they had to initiate the self-destruct sequence, costing $500 million. But the real kicker here was that the code wasn't needed. The code that was used in the Ariane 5 rocket was actually carried over entirely from the Ariane 4. It was believed that by leaving the code in, it was a less risky idea than changing the code, because it worked for the Ariane 4, so why not the Ariane 5? But the problem is the Ariane 5 was different. It was faster, so the numbers were much larger than anything they had expected when they wrote the Ariane 4, and it was never vetted for that. Now, the software here was written in Ada, where it's a language known for checking its type conversions, having stronger integer types, stronger floating point types, not letting these types of errors go away. But the Ariane flight team had certain performance requirements that they were trying to meet. And so they turned off checking in some cases where they felt it was going to be too much of an overhead. However, I think the real problem here wasn't with the integer overflow, and it wasn't with the lack of checks turning them off for performance reasons. I think the real problem was leaving in code that they didn't need anymore. They were too afraid to even remove code because of how difficult the process is of getting code validated, that they felt that it's safer to just let things be. You can see a full report of the disaster here. So let's talk about how you can avoid errors like this from happening in, or different types of errors from happening in C++. The first point I'd try to make is, let's say we have this point. You can construct it from two doubles. The first one represents a radius, and the second one represents the angle theta. So you're constructing a polar notation point here. But at some point during your software lifecycle, someone has a need for a Cartesian point, x and y. So you add it in and hit compile. Error, ambiguous overload. You have two constructors, both of them just take two doubles. The compiler can't tell the difference. So some people come up with this solution. It's referred to as the named constructor idiom, where you make your constructor private and you have public static functions that, in this case, say from polar and from Cartesian. So you can construct your point that way. However, I feel that there is a better way to do this. You can use C++'s type system. So you might come up with a solution that looks something like this. Instead of using double for theta, we just want to make the smallest amount of changes possible here. We create a new class called angle. But there's still a problem here. In 1998, NASA launched the Mars Climate Orbiter. The software on one end sent data in pound seconds, but the software was expecting data in Newton seconds. And so in 1999, the orbiter, instead of orbiting, turned into the Mars Climate Lander and cost $327.6 million. So when I'm trying to make a point, I can use from polar 0.0 pi. But as I'm sure many of your science teachers told you in elementary school, middle school, high school, pi what? Radians? Degrees? Pound seconds? Who knows? You need to have your units as part of your type. Units are an essential information if you want to prevent errors like what happened with the Mars Climate Lander. So we still have a problem, however, because people can use code like this. Point P, 1.0, and pi. They're trying to construct a point at pi radians and 1 unit out. But this is probably a bug, because what they're really doing is calling the Cartesian constructor, located at x position 1 and y position pi. This is especially a problem if you're retrofitting old code, as many of us likely are, because originally only the polar notation existed, code like this worked, and then you add in a new constructor, you notice the ambiguity and you solve it, but old code now becomes wrong. The interface is easy to use incorrectly. So we can create another class, say coordinate. Now we construct a point either from a radius and an angle, or 2 coordinates x and y. So now this code does not compile. The interface is difficult to use incorrectly. You have to call it like this if you want to do polar notation. Now, this example could be solved using boost units, but this is just an example. You might have types that aren't in boost units. You don't want to do any dimensional analysis on them. Let's say you're writing a video game and you're trying to construct a monster with a level associated with it. You don't want to just pass in an integer. You want to create a class for the level. Another issue with boost units, though, is that it uses double everywhere. So what happens if you want integer types, say in this example? So let's say we have this function, calculate. Takes an integer as input, but the integer has to be between 0 and 255. If it's less than 0 or greater than 255, then the function cannot work correctly. It cannot calculate whatever it has to calculate. Now, some people, when they're confronted with this, they think, oh, I know. I will change the type of the parameter of this function from int to unsigned char, or standard U int 8t. And then I know that the value is in range, because that type can only hold a value between 0 and 255. What happens if we do this? Suddenly there's no built-in type that lets us do that. But I think the real problem here is that we're trying to validate our parameters inside the function. So now users of the function have to know that there are preconditions on this input. If you just say int here and check the values, then this is something that can go wrong, and it will go wrong at runtime. So in general, you want to use self-validating parameters. For the specific case of integer parameters, I've written a library. I presented on it at C++ Now earlier this year called the Bounded Integer Library. And its goal is to make integer operations safe. General use case, you create about an integer with the minimum and maximum values specified at compile time. You can read more about the library at that first link if you want. But the important point here is that callers of the function see in the type signature exactly what the function expects. They don't have to read documentation. They don't have to guess. If they get it wrong, there's a compile error. Because the important point here is to report errors as soon as possible. A compile error is better than a linker error because it speeds up development time. A linker error is better than a runtime error because you don't ship linker errors. An error at object construction is better than an error at object use. That's what we were seeing in that function. If you try to detect integer overflow when you use the object, or you try to detect an invalid state when you use the object, it's already too late. Because the error happened some time ago. It may have happened 3 days ago when you constructed the object, and only now are you finally using it. A runtime error at object use, however, is still better than an error that goes undetected. However, this is not the only goal of strong types, just saying what you mean, documentation, creating compile errors to avoid ambiguity. Strong types also allow you to create an object that maintain invariance. So if I have a duck, it's a valid duck at all times. I can call duck.walk, duck.quack. It's all going to work. The constructor never partially initializes the object. I don't have to check duck.is it actually a duck. I know I have a duck, it works. So the general problem here is two-phase initialization. It's the same thing we were seeing with functions before. Now every time someone gets an instance of this bad class that requires two-phase initialization, they have to check, can I use it yet? And if you can't, what do you do? Do you throw an exception? Do you terminate? Do you write to a log file? All of these things are errors that happen at runtime when you could have caught them at compile time. Whereas if you have a good class, you can just use it. And going along with no two-phase initialization is no manual cleanup. So you never say delete. You use unique pointer t, or better yet, just t. If you want to know the reasoning for why I say use just t instead of unique pointer t, it's primarily performance. There's a full explanation here at this video explaining when you'd use dynamic allocation and when you don't. But the important point for this talk is that you never require manual cleanup of your objects. You never require manual unlocking. Use lockart and unique lock instead of using raw mutexes. Never require manual file closing. Use standard fstream instead of file pointers. The reason is that it's too easy to forget cleanup. It could be because of an exception. It could be because of an early return. It could be because of branching, or any of a number of reasons can cause you to forget to clean up. Or it could just be that someone is using your class and they don't know that they have to call cleanup. The technique is known as RAII, Resource Acquisition as Initialization. You might see some people refer to it as scope-bound resource management. The important point is you enter the scope, you acquire the resource, and it's automatically released. You don't have to worry about it anymore. It's one less thing that could possibly go wrong in your program. If you use unique pointer everywhere that you want dynamic allocation, then you will never have a memory leak. That's a class of bug that you've eliminated entirely. Another important class that I'd like to talk about is boost optional. It represents an object that might be present. It allows you to check, is there an object? You can get at the object with no checks. You can get the object throwing if it's not present, or you can get the object to the default. This is kind of the core interface of boost optional. It has a few other things like get the value or evaluate some expression and return that, but this is, I think, the central part of boost optional. And it's also been proposed for standardization. It's currently, some compilers, I believe, are shipping it as standard experimental optional. It's in what's referred to as a TS. That's a technical specification. It is an update to C++. It did not make it into C++ 14. It is likely it will be in C++ 17. But if you have a compiler that supports it, you can start using standard experimental optional now. It was only very recently voted in. Does anybody have any questions so far at this point? Just feel free to raise your hand at any point during the presentation. Okay. So the C++ standard has two pure reference types. When I say pure reference types, I mean the only thing that they do is they act as reference types. There's standard reference wrapper, and there's tref. The advantage of using the tref syntax, so it's been with us since C++ 98 and before, is the convenient syntax. If you have a reference to a class and you want to call a member function, you can just say ref.function instead of having to first get the object out of the reference and then call the member function on it. However, you pay for this convenient syntax with the loss of reference semantics with assignment. Assigning to a tref changes the contents of the object it references, whereas assigning to a reference wrapper changes, it makes it reference a different object. What this means is that you can store a reference wrapper in standard containers, unlike tref. If you try to say standard vector t ampersand, won't compile. You're not allowed to put references in standard containers because assignment doesn't, it's not a normal type, basically. Assignment doesn't work the way that you would expect it to work in the context of vector. You can also use standard reference wrapper in your classes. This can make your class assignable. If you have tref, the assignment operators are automatically deleted, and then you have to write your own. Now, the standard also has, or I guess C++ also has a few different ways to talk about optional references. There's boost optional tref, but note that this does not work with standard experimental optional. And there's boost optional standard reference wrapper, which does work with standard experimental optional. And the reason for that, again, goes back to confusing semantics with the assignment operator. The primary reason that standard optional or standard experimental optional does not have a specialization for tref is that it might confuse some people what happens when you assign to an optional reference. Does it rebind the reference to point to something else, or does it assign to the object that the reference holds? With standard reference wrapper, there's no such confusion because assignment always does the same thing. Now the third type, the third optional reference type in C++ is the one you're all familiar with, t-pointer. Represents a reference to t or nothing. And I would argue that if you do not mean that, you probably do not want to use t-pointer. A lot of times, especially in C++ 98 and 03, before we had standard reference wrapper, and when people weren't very familiar with boost reference wrapper, a lot of times if they wanted a vector of references, they would first try to make vector of tref, see it didn't compile, and say, oh, okay, I'll just put in a vector of pointers. But now you've allowed the possibility of a null pointer. Anytime you have a pointer, it might be null. You have to worry about that. And you can say, okay, I'll write my class to where I know that it's never null. But that's something extra you have to check. You've allowed the possibility of an error in the code. So now everybody reading the code has to consider that that error has occurred somewhere. Whereas if you were to use a vector of reference wrappers, that error is now removed. So that is why I say when you use t-pointer, if it does not mean an optional reference to a t, then you are likely confusing your users. With a few exceptions, which I will get to in just a second. In previous conferences, a lot of people have talked about the possibility of the standard adding a new pointer type, something like raw pointer or dumb pointer or non-owning pointer. The idea is that in legacy code, before we had moved semantics and unique pointer, a lot of people would use t-pointer as an owning pointer. So when you have a function that accepts a pointer parameter, you don't know if you're supposed to allocate it with new, or you're supposed to allocate it with malloc. Does the function take ownership of it or does it not, really is the question. So for a lot of code, there's ambiguity in what t star means, whether it's ownership or non-ownership. But now we have boost optional tref or boost optional reference wrapper. And that gets rid of any ambiguity concerns. We know that there is no ownership associated as soon as you say standard reference wrapper or tref. Now, there is one important concern here. T star on all platforms is the size of a pointer because it's a pointer. Whereas if you use standard reference wrapper, say you want to use standard experimental optional, and so you can't use tref, a standard experimental optional standard reference wrapper is almost certainly on all implementations going to be the size of 2 pointers, which may not sound like a big deal, but let's say you are writing some sort of trading program where you need to monitor 10 million symbols. And now each one of those, say, has an optional reference. That's 8 bytes of overhead times 10 million symbols. That's 80 megabytes of overhead throughout your system. That adds up. Or let's say you are writing for an embedded system where you measure the available memory in kilobytes, if you're lucky. Suddenly that 8 bytes of overhead adds up. It's just something to be aware of, and a reason that you might want to use tpointer to mean optional reference, even though there is that ambiguity concern. So I said that there are some situations where a pointer is not an optional reference. One of them is identity equality. When you compare the address of 2 objects, it tells you, are they the exact same object? Not just, do they have the same value, but are they the same thing? You see this sometimes in the implementation of assignment operators, where before they release their resource and take the resource of what they're being assigned, they first check, am I being assigned myself? The self-assignment check. Another thing that pointers give you that optional references don't is pointer arithmetic. However, I would argue you should prefer iterators instead. Use standard array iterator instead of using the decay from an array to the pointer to the first element, because then you don't lose the size. Use standard vector instead of a dynamically allocated array. It keeps track of the size and the capacity for you. And the other time a pointer is not an optional reference, as I mentioned, is new t, when the pointer means ownership. But we have standard make unique and standard make shared t. This means that there is no question of ownership. You see a unique pointer, you know who owns it. You see a shared pointer, you know who owns it. And you don't have to worry about delete. Goes back to earlier, no manual cleanup, because manual cleanup is a possibility of a bug. So strong types are your first defense. And just a general practice of trying to write code that you know can't fail, because all of the arguments to a function are valid for that function to operate. That still doesn't get you everything. Sometimes you have problems that you can't prevent at compile time. Let's say you are reading from a file and someone deletes the file. You are connected over an internet connection and the internet goes down. You allocate memory, but there's no memory available. So we need some runtime strategies. And there are 4 common strategies that you see. Return codes, exceptions, using optional or expected, and a global variable like in some C math functions where they set error no, and you have to check it. I'm not going to talk too much about error no. I'm assuming most of you already believe and agree that that's not a good strategy for thread safety reasons and just difficulty in remembering to check it. So I'm going to focus on return codes, exceptions, and optional. The error checking strategy that you use determines what you can do in your interface design. That has an impact on performance, on readability, usability, discoverability. So we have one option. Let's say we want to get a value that might or might not be present. We pass in the value by reference and return a bool saying whether we got it. We return by value, and we pass in a reference to a Boolean that we'll populate with whether we got it. We just return the value and throw an exception if it wasn't present. Or we return boost optional t, returning boost none if it wasn't present. So ask yourselves, which of these is easiest to use correctly and which is hardest to use incorrectly? So before we go into a deeper explanation of those, The traditional advice on exceptions is to only use exceptions in exceptional circumstances. If you go to Google and you type in, when should I use exceptions in C++, you'll get pages and pages of results of people saying this. But I say it's useless. What is an exceptional circumstance would then be your next question. And most places don't have an answer for that, or it's vague and not helpful. So I would instead argue that we should go back to the single responsibility principle. A function should do one thing and do it well. If a function cannot do that thing, it should not return normally. The function failed to do what you called it for, and therefore you throw an exception. One argument against this, fairly famous one, was an article titled Cleaner, More Elegant and Harder to Recognize by Raymond Chen, where he compared different sets of code. One of them used return codes for error reporting. The other one used exceptions. Now, his argument was that exceptions made the code harder to understand. However, I don't think that the problem in his examples was the exceptions. He divided everything into multiple categories. He said that code using error codes that's bad or wrong is easy to recognize. Code using error codes that's correct is hard to recognize. And code that uses exceptions that's bad or good is even harder to determine. If you see bad return-based code, he says, you probably know right away. It can be a little bit harder to make sure you got everything right, but most errors you can tell right away. And I think that's a good goal, to make wrong things obviously wrong. But when he claims that the exceptions made it harder to understand, I think actually the real problem was that he required manual cleanup and multi-phase constructors. That was the real source of confusion in his code. Had the objects cleaned up after themselves, rather than him requiring to call fclose and free and various other Windows API versions of those functions, then we wouldn't have to care so much about whether it returned successfully or unsuccessfully, because the objects would clean up after themselves. He had multi-phase constructors, so he would create an icon that registered itself somewhere, and then we set some properties, and then we set it visible, and then we set some other properties, and that would be fine in a single-threaded context, unless that last operation throwed because we set it to visible before it was actually done being used. But I think the real problem in his example was that he required the user, every user of the class, to get the ordering right, instead of just setting up the value correctly. But I think the most common objection to exceptions is that they're slow. And they are slow when you throw them, but they're fast when you don't throw them. Error code checking always costs time because you have that if branch. As soon as you say if in a program, that is one of the slowest things you can possibly do, because processors have pipelines. They might have, 3, 4, 8 instructions deep, maybe more, where they're executing stuff, and because memory is so slow, and because even accessing a register is so slow compared to just sending data through the processor in a single stream, they try to guess. They do branch prediction. They try to guess, what is this if going to do, so I can calculate what the result would be if I'm right. And then later on, I'll figure out if I was right, and if I was wrong, stop everything. Basically, imagine an assembly line, lots of stuff on the conveyor belt. They guess wrong, they have to stop the conveyor belt, take everything off, put on new stuff, and start it up again. You lose a lot of performance as soon as you say if. And error checking code is based around if on every function. Whereas with exceptions, there are no ifs. So all modern compilers use what's referred to as the table-driven approach, or the zero-cost model for exceptions. The one exception for that is Visual Studio on 32-bit Windows. If you're using Visual Studio on 32-bit Windows, I'm sorry, but exceptions are going to be slow even when you don't throw them. But Visual Studio on 64-bit Windows was able to break the ABI compatibility with a 64-bit switch, and they can use a zero overhead model as well. So I tested the performance of exceptions when you don't throw them. I just set up a fairly simple test case that involved reading and writing to volatile variables so the compiler couldn't optimize them out. And I looked at code that reported the error with return codes versus code that reported the error with exceptions, except there never was an error. I tested on GCC 4.9.2, and I had 3 test cases. No error checking at all, exceptions and return codes. When there were no destructors, there was a 12.8% overhead for exceptions relative to no error checking at all. But there was a 32.8% overhead for using return codes because of all those if statements. When I added destructors in, the relative number still remained the same, 6.3% overhead for exceptions versus 18.7% overhead for return codes. So exceptions can actually make your code go faster. As long as, and this is where the advice comes from for exceptions or for exceptional circumstances. It can make your code go faster as long as you're not regularly encountering these errors. Because as soon as we start throwing exceptions, as soon as we start encountering errors, then we get a 900% overhead for exceptions relative to, this should say relative to return codes. And a 750% overhead when there are destructors relative to return codes. So as you can see, there's a very big difference here. If you expect your errors to be uncommon, exceptions will give you better average performance. If you expect your errors to be common, then maybe you should rethink your program about whether those actually are errors or just a case that you don't like. So going back to our interface design, we have these 4 functions. The first function requires you to first construct a not really there t to pass by reference. It's typically implemented by creating a default constructor that does nothing. You basically make a duck that can't walk or quack. And then you pass it in by value, and then we make it actually a duck inside the function. What this means is that now all code that deals with your t has to deal with the possibility that it's not valid, because it is possible to construct it in an invalid state. It's possible that someone passed it in an invalid state. And it requires the caller to check the return value. In most code that I've seen, in most parts of the code, people say, oh, but I'm pretty sure that I'm going to get a value back here, so I don't have to check the return value. I'm just going to call the function and then use the value. We have similar problems with this interface. It requires the user to first construct a Boolean, then call the function, and then check its value. And contrary to what it might seem, it still requires the invalid state for t, because you have to be able to return a t even when got is set to false, based on the signature. This function signature is good if it is always an error for the value to be missing. The advantage is that there's no extra syntax for the normal case. Users using it normally, who don't expect errors, don't have to do anything special for the code directly using it. They can call the function, get the value to immediately initialize the value they want. There are some people who might be a little concerned here and say, what about this t here? Isn't there a performance cost there? Because inside the function, you have to copy it into the return value. And then outside the function, you have to copy that return into your local variable. And the fact is that actually, no, there is no performance overhead for that. There's actually a performance advantage over this type of function, because the compiler has 2 optimizations. It has the return value optimization, and it has move elision. So in the typical case, when you have this function here, if you directly assign this to a variable, and the function is fairly simple, where you do stuff and then at the very end you return an object, what the compiler will actually do is secretly pass in the address of the location the object is going to be constructed, and just directly construct it there. There are actually no copies or moves in the typical case for this. And it does even better than the function where you pass in a reference in some situations, because the compiler knows that this secret reference it passes in doesn't alias anything. It is the only reference to that location in memory. If you pass in a reference yourself, then sometimes the compiler has to be pessimistic. It has to assume that that reference to a t that you passed in is actually the same as every other reference to a t anywhere in the program. Or it isn't. It doesn't know. And that prevents several optimizations. So using this code in the normal case is just as fast, and sometimes it's actually going to be even faster than passing in by reference and populating the value. But as I said, only if it is always an error for the value to be missing. If you do not necessarily expect the value to be there, then you pay the performance overhead of an exception, which is significant. The fourth function signature, which returns an optional t, is good if it may not be an error for the value to be missing. The caller gets to decide. They can get the value without checks if they know by some other means that the value actually is there. Maybe they just put it in. They can get the value in a way that throws an exception. If they're not sure and they want it to be considered an error, they can get the value with the default. They can check if it's there and do something else. Otherwise, they have a lot more options. It means there is a little bit extra syntax over the exception case, but there are some interfaces where this is useful. For instance, consider the standard library function. Standard STUL, STULL, STL, various functions that convert strings to integers. Or for people not yet on C++11, the boost library function, boost lexical cast. The behavior of these functions that convert a string to an integer is that they return your integer by value, so they're using this signature here, and throw an exception if they were unable to convert it or unable to parse it. So they are making the decision that it is an error for you to try to convert a string that's not an integer into an integer. In some use cases, this is good, but in others, it isn't. So that leads to code that you see that says, try boost lexical cast, long angle brackets, open, and then my string, and then catch, and then return something else, or do something else in that error, when it wasn't necessarily an error for the string to be not convertible. And you could write a function that first checks if it is convertible, but doing that is essentially the same work as actually just doing the conversion, so you have to do it twice. Whereas if we had a function signature more like this, then the caller could decide. So when you're designing an interface, you may want to take a compromise solution. You can have a signature like this, throws an exception if the key isn't present. And a signature like this to get the default value. And then one of these two signatures to return an optional. The Boost property tree library is an example of a library that uses this sort of compromise solution. The advantage of the first two is minimal syntax for common behaviors. You want to make easy things easy. One of these two other signatures, either when the type specified is optional, which works for some cases and not for others, or you call a separate function named getOptional or something like that. That makes other use cases possible. Final line of defense, or another line of defense, I suppose I should say, is static analysis. The best static analysis tool out there is your compiler. It sees your source code every day. So there are, my philosophy on compiler warnings is turn them all on and treat them as errors. And then, when you find warnings that you don't consider to be useful, explicitly turn off those warnings. This is especially nice on compilers like Clang and Visual Studio, where you can actually specify, give me everything you have. Because what that means is that with a newer version of the compiler, you automatically get all of the new warnings. And if there's one that triggers on your code, you are forced to confront it before you can move on. So if it is an actual error that this warning has found, then you've just caught a bug for free without doing anything on your part other than upgrading your compiler. And if it's not a bug, if it's something silly, then you can add that to your list of disables. So when I compile with Clang, this is what I use. Turn on everything, but I don't care about C++98 compatibility. I don't care about exit time destructors. Implicit fall through is something that I should probably turn back on. There was a bug in the early implementation. And a few other minor things that I turn off. The important thing here, though, is the mindset that someone on the compiler team thought that this warning was important enough to write. Someone on the compiler team, very smart people, no matter what compiler you're talking about, looked at it and said, this might be a bug. This might be something someone doesn't want to do. And so I think if they took the time to actually write the feature, it makes sense for me to take the 5 seconds to evaluate it when it triggers. Visual Studio, use /wx/w all. One difficulty with this particular warning set is that the Visual Studio headers compile cleanly with /w4. That is one of their goals. It does not compile with /w all. So you can either take the approach, and I don't have a recommended list of warnings here to disable because there are a few different approaches you can take. You can use pragma warning disable around the standard headers because some of the things that they warn about that trigger in their headers could be actual bugs that you care about, especially if you're writing mission-critical software. So you can use pragma warning disable to specifically disable those warnings just for the standard headers, but not for your code. Or on the command line, you can just say, I believe the syntax is /w minus and then the number, to disable it everywhere. But as I said, it's easy to come up with your own list. Just compile. Now GCC, you want to turn on all the warnings. So you say -w error, -w all. But there's a few extra. And maybe you want to be pedantic about it. And maybe there's a few more. And a couple more than that. And maybe we keep going. Sadly, there is no way to turn on all warnings in GCC. I personally feel that this is a major oversight. The team isn't opposed to it. No one's gone in and done it yet. So any of you or me, whenever one of us has the time to do it, should go in and add a warning like -w everything into GCC. If you want a more complete analysis of the GCC warnings, there's a link to a Stack Overflow post. It actually goes through all of these warnings not covered in WAL, WExtra, WPedantic, and looks at some of the more controversial ones that are present that maybe you think shouldn't be there. I included reasons for why they are on my list. This is how I compile with GCC. And also a list of some other warnings that actually didn't make it on. There are more GCC warnings than this. This is not all of them by a long shot. There's maybe 10, 15 more of them that didn't make it onto my list, as far as I can tell. And it gives an explanation for why I don't include them. For instance, they have a W aggregate return. So if you return a vector by value, they give you a warning for that. But with move elision and the return value optimization, I don't consider that actually a problem. It's actually, I believe, necessary for writing safe code that doesn't rely on default constructors that don't do anything and passing stuff in by reference and checking to make sure it was initialized before you use it. But when you talk about static analysis, most people don't think of their compiler first, which is a shame. They think of static analysis tools. In my experience, it does not catch as much as the compiler. You have to do more work to integrate it with your build step than with your compiler. But it is a useful extra line of defense. I have looked at several static analysis tools. Some of them open source, some of them commercial, some of them fairly inexpensive or free, like CPP check, and some of them very much more expensive than that. And I have found CPP check to be by far the best non-compiler tool at detecting errors in your code. They are constantly coming out with updates. They have a Visual Studio plugin for all these other IDEs, or just a standalone tool you can run from the command line, friendly user interface, whatever you want to do. They catch a whole bunch of things that the compiler doesn't catch. Things like null pointer dereferences. I found it's better at that than any compiler is. But there are a few other tools you can use. One of them, a fairly new one, is Clang's, I believe it's called scan build, where you can run scan build and then make, or scan build and then scons, or anything like that, where basically it replaces your compiler with their special static analysis tool. So it's fairly easy to integrate with your build system. And it takes longer than a compilation step does, but it catches more stuff than just the Clang warnings. Visual Studio has a similar option from the command line. It's /analyze. You can access it just in, I believe it was added in 2010, but it may have been 2012. Yeah, the analyze tool, I found it's not as good as CPP check, but if you have Visual Studio and you have a new enough version, you have the analyze flag, you might as well use it. It does catch stuff. And I appear to be missing a slide. So one final line of defense in writing robust code is something that works with both GCC and Clang. They have a set of libraries that you can use when you're running your program. They're referred to as sanitizers. So there's the undefined behavior sanitizer. There's address sanitizer. There's, I believe, a threading sanitizer, where, for instance, undefined behavior sanitizer. Let's take that one as an example. You compile your code with the flag, use the undefined behavior sanitizer. You link to the undefined behavior sanitizer standard library, and the compiler adds in some instrumentation when it compiles your code. So if you have, say, signed integer overflow, which is undefined behavior, you get an error message at runtime at the exact point where the overflow happens. That says, hey, you have a problem here, undefined behavior. You dereference null pointer, hey, undefined behavior. They have a whole list of things that are not defined by the standard, but sometimes still works. Sometimes gives you the wrong results. Sometimes does self-destruct sequence on the Arion 5. Catches those errors for you. And in that same kind of idea, there are tools like Valgrind. Valgrind is a helpful tool, especially for detecting. I found the most helpful thing that it does is not the memory leak detection, which is what it's so famous for, because if you use unique pointer instead of new and delete, that's not such an issue for you anymore, but rather the detection that it has for overflowing arrays. If you read past the end of an array, that's undefined behavior. You run your program through Valgrind, which doesn't require any special compilation steps. You can take an executable that you already have. You don't have to change your build system. You run it through Valgrind, and it says, oh, hey, there was an access to memory past the end of your allocated region. You might want to take a look at that. So, in summary, you should validate your parameters using strong types. Use exceptions for error reporting. Use optional to avoid non-error error reporting. Only use optional types when you mean it, primarily pointers. Pointers are very much overused. A lot of times we use them when we don't mean optional. We just mean assignable reference. We have reference wrapper for that now. And turn on compiler warnings. They will catch things for you before your customers do. And use other third-party tools to analyze your code for the same reason. If you follow these steps, then maybe you'll be one of those people at the conference who's able to stand up and have a serious answer for whether they would be willing to be on the first flight of software that they designed. Maybe you will keep your own company off of the front page of the New York Times when your system explodes, or doesn't, I suppose I should say. Yeah, does anybody have any questions for me? Yes, do we have a microphone in here anywhere?
What do you think of Andrei Alexandrescu's expected T? Are you familiar with that?
Yes. So similar to optional, there is a concept from functional programming known as expected. I believe, I'm sure I'm going to butcher his name here, but Vicente Botet Escriba has been a strong proponent of the expected type. He gave a presentation about it at C++ Now 2014, earlier this year. And it gives you kind of a merger of optional and exceptions, whereas optional is designed for the case where a value might be present and it might not, and it's not necessarily an error for it not to be present. Expected either gives you the value or the error. So it is an error for you to not return the value, or for the value to not be present. And you are supposed to check the expected object to either get the value or handle the error. So the advantage that this gives you is that you can encapsulate the situation where it is an error for something to not be present, like exceptions. But in the case where the error may be a little more common, you don't have to pay the performance penalty of exceptions. And it also allows you to, unlike exceptions, transfer the error over, say, a module boundary. Typically, you can't throw an exception across a DLL boundary, whereas you can return the fairly simple type. So, yes, expected, I believe, does fill an important role. The disadvantage of it would just be the extra syntax. In the case where errors are expected to be very rare, I think the minimal syntax of exceptions helps prevent your normal case code from having to be changed by something that probably won't happen. So for instance, in the Haskell programming language, they typically use a type like expected, an either type, they call it. But for division by zero, they throw an exception. It's rare enough. They don't want to clutter up everybody's code every time they're dividing by anything for them to have to explicitly handle the error at that point. Does that answer your question?
What can we do if we have a library which sometimes returns or must return exceptions because we need the rich errors and need to handle them, and sometimes the client isn't interested in these exceptions. It just wants to know, okay, it failed or it didn't fail, and okay, we could write or do a wrapper and say, catch this thing and return a Boolean, but then we would pay every time for the exceptions if we are not interested in the exceptions. And but the exceptions are deep in the implementation. So is there a solution for such a problem?
So basically the question is that you're using third-party code that reports errors by exceptions, but for your case, you don't necessarily care so much about the exceptional.
No, it is if you sometimes care. Some of your parts of your program care about, and some parts of your program just don't care about them.
Okay. So In that case, I think the only thing you really can do is use something like I guess you have a couple of options, but most of them involve going back to whoever's providing you this library and getting them to change their code. Because if they say throw X, the exception is getting thrown. There's not too much you can do about that. But if they were to provide you more of a hybrid interface that throws an exception or returns an optional, and you can typically implement one in terms of the other to reduce code duplication.
But we would have to implement both pieces. We would have to implement a function which returns only the result if it fails or if it succeeded. And we would have to re-implement the whole thing to throw exceptions.
So one possibility, if you are the implementer, would be that you could write just the optional version and then write a thin one-line wrapper around it that calls the optional function, and if you didn't get a value, throw an exception, otherwise return the value out.
But you don't have rich exceptions then. If you pass a float, you could return an exception which parts of a float didn't pass or something. And if you only have true or false, you lose this information.
Mm-hmm. Yeah, that would be where like the expected type would come into play. The purpose of the expected type is that it can hold on to that exception information. And so in that case where you care about not just that an error occurred, but details about the error, like, oh, it happened when trying to parse this file and this line of the file, then you could do a similar sort of thing with an interface that either just uses expected and then have the caller have the extra syntax, but you have just the one function, or you have a function that wraps it and throws the exception from expected if you wanted less syntax.
Hi, thank you for the talk, very interesting. Just a remark on the last question. One example for this is the PowerPoint API, which I'm from ThinkCell, and we're quite familiar with the PowerPoint API. And they actually have a dual API where you have a raw function that returns an error code, and then they have a wrapper for this for every single API function that throws. So you can pick whichever fits your bill. And one obviously is implemented in terms of the other. I have another question. You seem to be, or you made a case for exceptions under certain limited circumstances. And one of your arguments is that you reduce the syntax overhead for the regular for the regular case. For me, that is precisely an argument against the exceptions, because problem is that in rare cases in cases where errors are very rare, the code is mostly untested, the error handling code, because it is so rare, it's implicit. And with the exception, it also becomes invisible. The exceptions add a code path that is not explicit to the client, to the user, to the programmer. And the combination of being an invisible code path and a code path that during testing never runs seems to be a very dangerous situation.
Yes, so I agree that if you never test your error handling code, like most people don't, then you are in a pretty difficult position. However, I also believe that what exceptions a function can throw are part of its interface. They don't necessarily appear in the code exactly, but you still have to know under what circumstances can this code fail. Sometimes, maybe even most of the time, unfortunately, I feel like people use exceptions as a way to handle the error or to report the error, but the users of the function don't actually know what can cause this exception to be thrown, or even what exceptions can be thrown. So I do think that is important. And unfortunately, as far as I know, there are no tools to help out with that. You just have to read the documentation and hope that they document it. I think that a useful tool for making code with exceptions easier to read and to make sure that you're handling them appropriately, just as a starting point, would be one that essentially generates an exception specification, not as something to be part of the code, but something for documentation that you generate that you can look through and see, oh, okay, this function can throw these exceptions. And hopefully they're descriptive enough that you can figure out what you have to do to either make sure that those exceptions don't happen, because a lot of times exceptions aren't random. It's you give this input, it's not valid input. Sometimes it's difficult to encapsulate that in the type system if it's, say, 3 parameters that all can't be something. It's difficult to make a type that supports that in some cases. Then I think some sort of auto-generated documentation would help make that more visible. However, I also believe that, at least for me, I can only hold so much code in my head at one point. And if every level of function call is 2 or 3 times longer than the code that actually is doing something, if the majority of the code is error handling, where all it does is pass the error up to the function that called it, I don't feel like that's gaining you anything either.
Hi, I have one question. So you said you should favor to handle errors that are expected, not with exceptions, but what do you do in the constructor? If you expect the constructor to fail, but you cannot do anything except exceptions.
Okay. So in that case, I think that is where the best solution would probably be to one of 2 things. Let's say you want to construct an object from a file. And maybe the failure is that you have some sort of arbitrary file system error in the middle of constructing the object. Typically, the only way to report that would be to throw an exception. But let's say this is an unreliable file, or it's on a network file system on an unreliable network. You don't want to necessarily throw an exception for something that you think has a pretty good chance of happening. In that case, you could create a function that looks like, make my type, and it returns an optional t, and it parses information out of the file and passes the stuff it needed to pull out of the file as separate arguments into it. So like, let's say the file, you need the information on line 7, 18, and 23, then it could pass in those 3 strings as an argument. And now the constructor can't fail, and you have a function signature that says this object may or may not be present, and properly indicates that you have to check for both cases without giving you necessarily the performance drawbacks of common exceptions or the overhead of try-catch blocks for common exceptions.
Hi, I've been thinking about similar ideas too lately, mainly strong types and error handling strategies. But I think these 2 things doesn't fit well together, because I'm still using the old standard, so we have our custom optional type, and either you go for dynamic allocation, or you need your types to be default constructible. So that's the duck that cannot quack. Throwing an exception has another issue, that your local value is limited by the scope of the try block. Again, I was not able to come up with a better solution than dynamic allocation. Maybe you have some good, reasonable advice.
Okay. So even if you are on the older version of the standard, boost optional is compilable with fairly old compilers. I don't know the actual compiler requirements. I mean, I don't know if they support, like, say, Visual Studio 6 or something like that. I don't know how old of a compiler you're on, or maybe an embedded system compiler. That would be what I look for first. And if that type of solution is unfortunately not possible, then I think a unique pointer is probably the only solution that's really left, but then you pay the cost of dynamic allocation. That is if application safety is your primary goal. Now, it is possible that in some situations you're willing to sacrifice that safety for some performance. But I think you have to be careful with that. My boss likes to say that I can make code run as fast as you want if it doesn't have to be right. So, by allowing the code to be wrong with a default bad state that you then fill in later, it's possible that somewhere else your code would be wrong where you didn't expect it. That'd be my only caution there.
Actually, is to follow the remark of the other sir, I think is in the Ariane 5 problem, it was also a global design issue. It's not normal that a single part can overflow your whole system, that you need to crash, because the system crash anyway. So I think now one of the biggest issues is that the system is so complex that you cannot have this global view about, like, a single part can actually completely overfill a bus. And so how do you actually try to keep track of this global view when every independent part can be like kind of contained if something is happening? How do you do that? I don't know.
Mm-hmm. Yeah, so I think it is difficult. The software that we write today probably has about as many bugs as the software that we wrote 30 years ago, because the software that we're writing now is so much more complex than it used to be. But I think that the advantage of tools like static analysis tools in your compiler is that they can have this global view. They never forget something, they never make a mistake. They can scan thousands, tens of thousands, 1 million lines of code, and they always look at it with the same level of intensity. But I think the most important way to improve the reliability of a large system is to avoid large systems. And I know that sounds like a joke, but so at my work, when I started, we were on Visual Studio 2005, and we had a code base that was 20 years old, and it had grown over time. And we were kind of like the Ariane 5 team, where we had systems that had to be up 24 hours a day. We handle the full financial information for essentially every exchange around the world. And we power some of the top websites in the world where users expect to be able to go there and always be able to get the price for their symbols. So we can't go down. So that made people afraid to remove old code. But what I saw happening was that we were starting to get into a situation where almost every change we made failed. It caused an interaction somewhere else in code that we thought no one was using, but they really were. And so over the past 2 years, my colleagues and I have been having a competition. We measure our productivity not in lines written that week, but in lines deleted. Every time we add a feature, we take the view that all code is a potential bug. Every feature is a potential defect. And so every feature that we add to our product is negative points. And to be able to pay for that, to offset it, you have to remove something else that we don't need anymore. simplify something else that nobody's using. Prefer standard components instead of home written. I don't know how many linked list implementations I found and got rid of and just replaced with standard vector. To where I think in the past year and a half or so, we've probably deleted somewhere on the order of 50,000 lines of code. And our systems run faster and they're more reliable as a result. So when I say avoid large systems, it's use standard code, and you'll often find that your code gets smaller. If the code that you're writing is only your business logic that you care about, that's the stuff that you are most qualified at looking at and making sure it's correct. Like, we all like to think that our problems are so difficult that we need to write all of this code. But when you really boil it down to its basics, most applications are fairly simple. And sometimes we have to write code to work around bugs in the compiler or performance problems in the compiler. But oftentimes these bugs and performance problems don't exist in the compiler anymore. You know, we upgraded from Visual Studio 2003 to 2005. A lot of code was made obsolete from that. We upgraded from 2005 to 2012. A lot more code was made obsolete from that, but nobody went back and deleted all the old stuff. And so our system got big. Our focus now, make the system small. The smaller your system is, the less surface area there is for bugs.
I just want to comment this because we were in the same situation. So there are tools for this as well to find code duplicates or unused codes.
I'm sorry, could you say that again?
Oh, sorry?
Could you repeat that?
Yeah, we were in the same situation. It's a huge program, a huge application developed over many years. And we clean up, it took some years, the code, and we are still cleaning up. And there are some tools for this as well to find code duplicates or to check the code coverage and things like this to support you.
Okay, I think my time is just about up here. So if you want, you can come up and talk to me. I'll hang around. But I think that's everything I have to say.